But there is one condition. Yeah. Unless acted upon by an unbalanced force. That's the first law of motion. It's also known as the law of inertia. I'll put that in quotes at the bottom. Law of inertia. All right. So a good way to think about really what the law of inertia is getting at is, whoa. I'm sorry.
So we can't do this.
Good way to think about this is if you're driving in your car and you got a cup of coffee. I'm going to draw 3 cups of coffee right now. You don't have to draw all of my little, I'm just kind of having fun up here. So if you are accelerating in your car, so I'm going to draw some dot diagrams here. Oops. It doesn't want me to, it's not letting me draw dots because it thinks I'm trying to do something else. If you are accelerating here in that direction, and this is the direction of your motion, you're driving this direction. If your acceleration is in the same direction as your motion, your coffee is going to slosh up over here, isn't it?
Yeah.
And then it's going to spill on your lap, and you're going to have to wash your pants. But then after you get going, once you're going 65 on the interstate, your coffee stays exactly where it is. And then when you get to your exit at the last minute and you realize that you're supposed to get off and you slam on the brakes and get in the right lane, your coffee goes like this. When your acceleration is in this direction, your coffee sloshes out of the cup. So this is exactly what Isaac Newton discovered. He was the first person. I mean, it's amazing. Like this is so obvious. We all know this. But he was the first person ever to write that down, and no one believed him for the longest time. But he's right. So an object, this is basically a balanced force. Here you have an unbalanced force over here, and a balanced force here. The reason why it's called the law of inertia is because, let me define inertia for you. Inertia is the tendency of an object to resist change. How's that? The tendency of an object to resist change, and it's based solely on mass. Solely, is that how you spell it? Based solely on mass. Yeah. So, for example, if you, if you kick your car when it's in neutral, it might move a little bit. And if you kick your soccer ball, it's going to move a lot of it. Even though you're giving it the same amount of velocity, it doesn't matter how hard you kick it. It matters on the mass of the object. The car has more inertia. So it has a higher tendency to resist change than the soccer ball. If it weighs more, if it has more mass, it's going to have a larger inertia. So don't get it confused with momentum. Momentum has to do with velocity. Momentum is the product of mass and velocity. Inertia only has to do with the mass. So let's talk about what I mean by unbalanced forces anyway to begin with. So let's just say you have a textbook. Let's make a table here. We got a table. This is your physics table. And you have a textbook sitting on it.
That's a big textbook.
Yeah, this is your AP history. There's a force acting on it. There's the force of gravity. We all know that. The force of gravity is in a downward direction. So, why doesn't the book fall through the table? The table is also putting a force on it. We call that the normal force. There's a force upwards of the same magnitude as the force of gravity. And we call that the normal force, F sub n.
Should we draw this?
Yeah. That's called the normal force. So if an object is not accelerating, then the forces must be equal. Let's draw, and then if you give that book a little push, let's just say you push the book to the right, so the book has some sort of rightward velocity. There's going to be another force over here. The force of friction is going to be resisting it. The book is eventually going to stop sliding across the table because the force of friction is there. And then once the book stops, the forces will be balanced again. And we have all kinds of different forces. Like, for example, you can, let's just say you hang a bucket from a pole. It's art for me. You hang a bucket of water from a tree. The bucket is not moving, so the forces must be balanced. There's definitely a force of gravity. We all know that. F sub g. And then you have a force that's keeping it up this way. That's the force of tension. F sub t, that's a new one. The normal force is the force of the ground on an object. Always. The force of the ground, or the table, or something like that. Tension is something different. Different force. And this is called a free body diagram. When you draw the forces that are acting on an object, we call that a free body diagram. And free body diagrams are very important because they allow us to assess all the forces acting on an object before we start to do any sort of computation. So right now, it's pretty intuitive, but eventually free body diagrams will be a very important tool. So it's a very important thing to know how to do.
What's the F of T mean again?
Force of tension. Newton's second law of motion says that force is equal to mass times acceleration. So for example, if you're standing on a scale in your bathroom because you're on the wrestling team and you got to know how much you need to throw up that day.
A good bit. You say like twice? At least.
I could never be a wrestler. You're standing on your scale and it gives you a weight.
Mind over body.
Weight is the force of gravity. So if you're standing on your scale, the force that it reads you is your mass times 9.8, because your scale gives you a positive number, so that's why I'm using the positive value for gravity. And you could do, the same thing for everything. If you're if you got a big truck and it's slowing down and you want to know how much braking force you need. The force, if you need to decelerate in that direction, the force of friction is going to equal the mass of the truck times the acceleration due to friction. Every single case, force equals F times A. And again, Newton was the first guy to figure this out. It's such a simple thing now. We all know it. It's just like so obviously true. But you got to understand, back in the day, they had no idea. And now we know all this stuff, and we can do all these cool things.
I wonder what made him think to actually do it.
He was just a curious guy, I guess, You guys seen the things in the back of trucks now that go like that?
Oh, yeah.
To cut down on the drag? That's another force, the force of drag. F sub, sometimes you call it air resistance, sometimes you call it drag.
Mr. Holt,
Yeah.
what's the force between the truck and the trailer?
The force between the truck and the trailer?
What's the force?
That'd be they call it a contact force.
Oh, contact.
Or applied force.
There's not a lot of contact force.
That'd be an applied force.
So just that's all.
Cool. All right. So I think that's the end of art session. And let's, you guys want to draw another picture?
Yeah.
Yeah, but when it's needed, not just random.
Okay. Let's take a skydiver. This is a common one. If you're, just anybody in here go skydiving?
Yeah, all the time.
I did. I told you guys that, right?
Yeah.
My last day of high
We
school.
got super jealous. We were like, oh, Mr. Hall, you're so cool. Will you take us skydiving? You were like, oh, no, this is my job. So he's not skydiving,
That's
it's
what
free
you look
fall.
like?
Like he fell out of a plane.
Oh yeah, he's not opened his parachute yet. Yeah, he's falling.
He just went with it, huh? He flew. He
Oh,
came
he's
down.
looking up at the plane because he's like, yeah, I like my parachute.
Oh, the parachute's not on.
Can you make us scared?
So the force that he's gonna hit the ground with is going to be force his
Wait,
weight
no.
and
Oh.
gravity.
Let's draw a couple free body diagrams. When he starts to fall, he's only got one force. I mean, he's got a big force of gravity. He's got a big F sub g, and he's got a small force of drag.
That's the wind.
That's the wind. But then after a couple seconds, you reach terminal velocity. Terminal velocity is when your forces of gravity and drag are balanced, and that's the point where you can't go any faster. So after a couple seconds, his F sub g, his force of gravity, and his force of drag are the same.
Wait, you put S. Yeah, you wrote
Oh.
FFG.
Yeah, you know what I mean. Force of drag.
S's.
And then you have balanced forces.
Hey, Mr. Hall, you were bald when you went skydiving?
And remember that, hold on one second. Remember that force equals mass times acceleration. So that makes sense because when you've reached terminal velocity, you are not accelerating. Your force is constant because they're balanced. Your mass is the same because your mass isn't going to change when you're skydiving. So your acceleration is unchanging. It's zero because you're going at constant velocity. You've reached terminal speed. There is force. That's a balanced force. There's no acceleration. All right? We lost a couple people back there. Let's cut it there.